to enjoy lunch, and we have Dr. Noboru Matsuda from Carnegie Mellon University, and he graduated from University of Pittsburgh, and he specialized in intelligent literacy system, and did quite many interesting things, and especially did something called the simulated student, and this kind of system he designed, and also get National Science Foundation support. So we are going to listen to his talk and get some idea about his work, and welcome.
Thank you so much. Howdy.
Howdy.
Thank you. That's the first Texas language I have to learn. My name is Noboru Matsuda. I came from the Pittsburgh, Pennsylvania, working at the Carnegie Mellon University in computer science, Human Computer Interaction Institute. Today, I will be sharing with you our recent research findings of achievement on a pedagogical agent called SimiStudent. I will be sharing how SimiStudent will help students to learn, and also how SimiStudent helps researchers to do research in education. So it's a methodological challenge. Okay. This obviously is the collaboration with all these people, including two of my kids, who are always the first participant to the study, right? Like pilot study. So anyway, right. I would expect an hour for the talk today, and then you are welcome to ask questions if my English is not that clear, which happens always. And then I understand we have like a half an hour QA session after this presentation, so you can split your questions into two things, right? Okay, so now challenges in educational studies. As many of you know, it is hard to run a tightly controlled studies in the classroom. Why? There are so many factors you want to control, right? Then also you always have a limited resources you can use, like the number of students, number of classes you can go, right? It's always limited. You have only limited times to run things, right? Ethical issues. You cannot be a mad scientist, period, right? You gotta be a nice scientist, right? But sometimes you want to do some kind of challenging research, right? Which may or may not be okay to run in the classroom, right? Collecting detailed data is hard, right? It's just simply, right? Interaction between students and teachers, among students, it's simply too rich to collect, right? It's not always that easy. Conducting reproducible research is also hard, right? So imagine you do some research, takes you maybe a couple of years, you are exhausted, you have some conclusions, you write a paper, that's it. You're happy, right? You may not want to do that again, right? However, reproducing what you found is really important, right? But it's not that easy. It's not that motivated to do, right? So these are all challenges for the educational studies, okay? We do know they are all important, but we don't know how to make this, right? It's always painful. Challenges in educational technology. I identify myself as a nerdy learning scientist, right? I do technology for the science of learning, okay? So I know the challenges in digital technology. Creating online the technology is hard, okay? Because we do not exactly know how to design things, how to make it, right? There are principles, but they are not exactly operational. By this I mean, trust me, if you make something first time, it's always failing. no matter how carefully you design it, no matter how hard you study literature, the very first version you make is always failing. Okay, so it is hard to make something that works on the fly. Okay, we do not actually have any technology. Let me back up. We do not have that many technologies to build things, right? So the authoring here is always right the issue, right? It simply just takes time, right? We need few programmers to work full time, right, for maybe years, right? As a consequence, we need always the iterative design improvement. You do something, you just run it somehow. You got some data, right? And then you identify issues. You make evidence-based the proposal for the system revision, right? So you change your system, you run it again, you collect the data, just repeat this 5 times, 10 times, right? So it's an iterative process. It's really, really painful. Okay, it really takes time. And an iterative process requires data, which is hard to collect, as I mentioned in the previous slide. Okay, so these are all challenges. All right. Now, I am a optimistic person. Yes, we do have solution here. All right. So the solution here is a simulated learner, which is the simulation of the learning processes that allows the researchers, right, to do some educational studies. All right. So back to 1994, 20 years ago, Mellon, who is my teacher's advisor, said the technology for cognitive simulation of learning is now ripe for application. 20 years ago, he said we can use computer to simulate things, right? Now, so some promises, okay? So advanced theories of learning and educational technology, right? The simulated learners may allow us to run tightly controlled studies. I'll mention this soon, okay? They also may let us easily to run things repetitively. Also, it's IRB free. Okay? You don't have to get IRB if it's computer. Okay, that's beautiful, right? And then it also facilitates us to get a fine-grained data. It's just like this, to get the 1 gigabyte of data, right? Okay. And then also, because of this data, right, we can easily do this iterative design process, okay? Interestingly, this is one of my main focus today. I will demonstrate to you that now we can actually use this student in the classroom for in vivo study, and obviously in the lab study, right? The both. Okay, so the simulated technology is really mature. That's my kind of primary claim here today. So these are the few examples of the simulation studies, you know, since 20 years ago, right? You don't really have to read all these. By the way, I'll be happy to share my slides today, so let me know if you need a copy. Teacher training, right? One thing. We have a teachable agent. This is part of my talk today. We have intelligent authoring. You can make a computer tutor by teaching computer. Okay, that's intelligent authoring. That's part of my talk today also. Formative evaluation and then prediction, right? You can predict students' learning, right? Like a formative evaluation prediction. Crash dummy test. Crash test dummy, this is my favorite. Because it's computer, you can really be a bad scientist. Okay, you can crush them by teaching badly on purpose to see how badly they learn, they fail to learn. Okay, so it's crash test dummy. You know that crash test dummy in the car? You put the dummy in the car and crash it, right? Same way. Okay. The student modeling and then the intelligent tutor, right? That's another application for the simulated learner. All right, so of course there are assumptions. Okay, I would claim that to advance theories of learning sciences, simulated learners must be a computational model of learning. Okay, no cheating, please. Okay, with a cognitive fidelity. This is my claim today, all right? And I demonstrate, I prove you this is correct. Okay. I also think that simulated learners with cognitive fidelity would generate authentic simulation data that better explains students' learning. Okay, so this cognitive fidelity is really a key today. Okay, then we can collect data. Okay, using this technology. All right. So the primary research questions for the talk today is this: how do simulated learners help education research advance theories of student and machine learning? Okay, so it's kind of both education and then computer science. Okay, machine learning is a hot topic in computer science. How do simulated learners help education researchers conduct the rigorous educational studies? Okay, this is the methodological point of the talk today. All right, so now, so far so good? So our solution is called SimStudent, okay? SimStudent is a computational model of learning in the form of inductive induction, okay? It inductively learns skills when you teach, okay? So it's an induction. It learns productions from examples. Okay. So how many of you have no idea about inductive learning? Little bit of inductive learning here. Okay. So use examples. You induce the general the principle behind. Okay. So that's induction, right? So and then you basically make productions saying, if I see this, I do that. If then, right? That's the production. Okay. So and then if you apply chain of productions, if I see this, I do that. Now I see this, I do this. Now I see that, I do this. Right? It's a chain of production application. That's how you solve problems. Okay? Clear? Just ask me questions if it's not clear, all right? Trust me, once you lost today, you lost forever. Okay? So my talk will be just boring. All right? Just ask questions. All right? So the production says basically it basically says if I see this, I do this, right? So it has three components. Where to pay attention if I see, right? Pay attention. This, right? What, how, right? How to make an action, and then when. I'm sorry, I screwed up. Let me back up. Production says if I see this, I do this. If I see this, part two components. Attention, and then condition. Okay? I do this, part has how, right? How to make the action. Okay? It's where, how, and when. Right? Example. Example always helps. Okay? So suppose this equation, right? I now teach SimStudent how to do this, right? So I get this problem, equation. I just said to SimStudent, you subtract 1. Okay? At this moment, this is an example, right? From this example, SimStudent may say, okay, when I see a polynomial in this left-hand side, and another polynomial in this right-hand side, then I subtract the last term, which is 1, right, of the left-hand side. Okay? So that's if, then, right? If I see this, then I do that. All right, so now here, this left-hand side, right-hand side, that's the where part, right? This is the where I should pay attention. This red, they are polynomial. That's when part, right? And then I subtract the last term of this, right? That's the half. Okay, clear so far? All right, now. Inductive learning is really, really tricky. Okay? How do you know this one is this No way, right? No way. If you, okay, just imagine you see this first time in your life. You have no idea about algebra, right? You have no idea about the equation. If you see this, what would you say? You may say, oh, I subtract difference between 4 and 3, period. Right? Which is what? Right? If you do not have any background knowledge, right? Or you may say, oh, I subtract the coefficient of this term, which is what? Okay, so that's the beauty and also the trick of the induction. Okay, there is no way to test the hypothesis up front. You may just make make a hypothesis. You keep it unless it flips. All right, that's induction. Good. All right. So just to talk about a little bit about the computer science thing. It turned out making this kind of induction is pretty challenging. And then it took me 3 years plus alpha to make this technology. And then I used 3 AI technologies, which is called version space, to learn this part. And then the inductive logic programming to learn that part. And then the iterative deepening depth first search to learn that. Okay, these are the technology behind, computer science technology behind. Okay, now, yes, please.
If you knew those were polynomials, then they're both polynomials, and you just use a polynomial solver.
Right. Yes. So that's nice point. The question is, how do you know this polynomial?
What is the background knowledge?
Yes.
That you're assuming?
Right. Yes. It will come in 2 slides.
Okay.
Yes. Very nice. Thank you so much. Right. The question is, how does SIMI student understand this is polynomial? Right.
No.
Oh no. Yes.
What was it given to start with?
I see. Right. So right. I meant that, but in a different way. Right. So I'll answer the question. Right. So
did it know that it was trying to solve equations?
Actually, it's depending on the definition of solving equations. SIMI student does not actually know the goal here, unless you teach. I'll cover that one later. These are the design the assumptions. When I design SIMI student, I hypothesized or I assumed that the students learn skills as productions, as I mentioned, if they're productions. Okay. Students induce productions from examples. They need positive examples and negative examples. They have to be told, you should do this, which is positive examples. They also have to be told, you shouldn't do this. That's negative examples. Okay. Without negative examples, you actually do not actually learn things accurately. Meaning, don't just be shy of making errors. You have to make errors to get negative examples. I'll come back to this point later. Induction is made for individual productions. This is a key assumption. Okay. So you gotta be focused on a particular production to learn that production. Okay. Now, induction is driven by prior knowledge. Yes. So domain-dependent features and operators necessary to interpret examples. So this is part of your question, right? So yes, SIMI student is given a bunch of prior knowledge to interpret the examples, to understand the examples. Okay, so here. Oh, you know what? Actually, I do not precisely have the answer for your question, but so these are the prior knowledge I gave to SIMI student. So SIMI student can understand what polynomial is. So I gave SIMI student like 27 features. This is one of 27. SIMI student can understand polynomials. SIMI student can understand monomial, fractions, right? Negative terms, positive terms, all these are the language to represent the features. Is that point clear? Is it answering your question? Hopefully, right? And then Symistudent also know all these primitive kind of operations, right? How to get the last constant term, right? These are the features, I'm sorry, the part of the background knowledge that Symistudent has. So, in other words, roughly speaking, what Symistudent is doing is, given all these language or the terminologies, Symistudent try to make a combination of these terminologies to explain the positive and negative examples. Does that make sense? In some sense, that's what Symistudent do, right? It's all about searching the combination of a meaningful explanation for the positive and negative examples, all right? Okay, good. So now, so is it actually answering your question?
Not yet, but.
Not yet. We can talk more later. Okay, good. So now I know I am a great presenter here. I will do the live demo. Okay, so often fails, but we'll see. All right. So now, okay, so we'll see. Okay, so yes, this is it. All right. So this is a demo. All right. So in this demo, I already, where's my cursor? Oh, right here. Okay, right here. Good. So here, okay. So this is a communication channel between myself and the Symistudent. Okay? This is called a tutoring interface. Okay? This is an interface I tutor Symistudent. I'm going to demonstrate that I can tutor Symistudent. Okay? All right. Now here, this is risk technology. Okay, so I just turn on Symistudent here. Okay. Now, all right. So I turn on Symistudent. I will start from. Oh, let me back up. I forgot one thing. All right. So this is a situation where I hypothetical myself, who is a math teacher, wants to build a computer tutor for my kids in the classroom. Okay. However, as a math teacher, I don't know how to do programming. Okay. However, I can teach Symistudent how to solve equations. Okay. Oh, this is I'm dreaming to make this computer tutor for equations. Okay. That's the background story here. All right. So, as a math teacher, I use this cognitive tutor authoring tools. Okay, it's too small. Cognitive tutor authoring tools. Okay, this is a tool which is available public. You can download this. Using this tool, I already made this interface. Okay, making this interface is just simple. It's just putting boxes, labels. That's it. If you can make a PowerPoint slide looks like this, you can do this also. Okay, it's really the cut and paste. Okay, drag and drop. Okay, it took me 5 minutes to make this action. It's not easy. All right. Once I have this interface, now I use this interface to teach Symistudent. All right. Okay. Good. Now let me see if I can do that. All right. Start from what about 3x equals to 5? Or is it too small? Hopefully not. It's okay. Is it okay thing? Okay. So I enter 3x and 5 here. Okay. Now here, I say Symistudent. Okay, so this is the first program. Okay. All right, first problem. Now I start teaching Symistudent. Okay. I say, look at this. Remember where to pay attention, right? And look at that, right? And then I say you have to divide by 3. Okay. And then I hit enter. All right. This is the first step, right, to solve equation, right? The step is visualized here. Okay. Now, remember my assumption: production is learned for a particular production, right? So I name this production. Okay. I say, Symistudent, this production is called divide. Divide. Okay? Name doesn't really matter, it's just a label. Okay? Now I specify this first production as a divide. Alright? So I'll come here, alright? So now CB student, right, look at this. Look at that. Now you divide 3x by 3. Now you got x. Alright? So now I come here and then I name this separately because I believe this is different production. Okay? So now I say divide type in. Okay? At this very moment, CB student learned two productions, divide and divide type in. Okay? Now I say here, look at that, look at this, and then here it's 5/3, right? Now I name here, and then tell CB student, you know what? This is the same production. Okay? So I just pick this, and then just tell CB student that's the same production. Alright? Now I say, look at that, look at this, and then now it's done. Problem solved. I click this. Okay? And then I name this. This is another production, right? To know when it's solved. Right? And then I say it's done. Okay? Alright. Right. So back to your question also. CB student does not really know the goal here until I say that's the goal statement. Right? I say it's done. But this is the goal.
Wouldn't you label it QED?
Oh yes, no way, because it's hard coded here. It's genetically coded that way for CB student.
Done.
Done is done. Sorry, I'm not a mathematician. All right. So now, okay. So what's interesting here is that CB student learned 3 productions. Remember? Okay. Now, because production rules are behind the screen. Okay. Now, and also because I have this interface. All right. I'll come back to this point later. But if you put interface and productions together, that's cognitive tutor. All right. I'll demonstrate that also here. Okay. Now I'm switching my demonstration to demonstrate this is actually the working tutor. Okay. I'm done on authoring part already. Okay. I already have cognitive tutor here. Okay. This cognitive tutor works only this type of problem though. Only division, that's it. Right? I'll demonstrate that part, okay? So now I come here. Now I turn off CB student. Okay, I turn off CB student and then I go to cognitive tutor. Okay. Now here, now I say, okay, this new problem. Right? New problem. Okay. Now here, so what do you think? What about like 7a equals to 2, for example? Right? Okay. And I say here, that's the new problem. Okay. Now remember, I am demonstrating that this is actually the cognitive tutor. Okay. Now, I'm a student here, right? I'm using this tutor. I said, okay, can I subtract 7? Really? So this is the beauty of live demo, right? I'm supposed to see this is red. Oh, no, I'm sorry. I just simply made a mistake. Let me just fuck up. No. Okay, so I'm not. Okay, let me just. Okay, I just forgot to turn on one thing. Let me just back up here. All right, so I'm demonstrating that's why. Okay, let me back up here. All right, so it said no here. Okay, keep this interface. All right, sorry about that. I say. Whatever, 7a equals to 3, right? And then I say this is a new program, right? P3. Okay, now I should say I test tutor. I'm testing tutor. That's the piece of puzzle I forgot. All right, so I'm not testing tutor here. Okay, now say here. Now I say add 7. Red means it's wrong. This is one of the features of the cognitive tutor. Cognitive tutor is simple tutor. It says only correct, incorrect. Okay? And then, because of the production, the cognitive tutor knows what should be done next. Okay? So, if I ask for help, that's what cognitive tutor says. Yes?
What's it? It's tutoring me.
Yes, now tutoring me. Yes.
And my guess is that my guess is I add 7. And it says no.
Right. right? So
Yeah.
tutor is wrong.
So I would
Right.
say, I would make another guess.
Yes, exactly, right. So I can say here, for example, I can say come back here. Okay, so I can add 7. What about divide 7? That's green, means it's correct. Tutor says it's correct because of the productions behind the screen. Isn't this beautiful? Right? And also, if I ask what should I do next here, right? The tutor says, so here I say, help me. Tutor says, enter A, right? Which enter A, right? So A is the next step, right? So, so I can enter A, right? So this is basically right. And then if I ask again, the tutor says 5/7, right? It's 5/7, right? So tutor knows how to solve this problem. Only this type though, because this is the type, only the type I tutor student. Okay. Now, any questions so far? I know I have to speed up here. Okay. Now, let me just do another demonstration here because it's important. Okay, so I go back to, okay, I go to next problem. I turn on simulation once again. This is simulation on once again, okay? All right, so now here. Now here, what about I say x minus 3 equals to 5, okay? And then I say this is another problem. Now this time, I will ask semi student to solve the problem instead of me demonstrating, okay? So I say semi student, okay, I say semi student to solve this, okay? So I click here and then say solve this, all right? Now semi student said, I entered divide 3 here because that's the only knowledge he knows so far, right? And he's asking, am I right? Okay, so I say no, it's wrong. So I say no here. Okay. Now the student said, I entered. Oops.
You said yes.
Oh, did I say yes? Oh, I screwed up already. Okay, so imagine I said no already. Okay. If I have said no, student gets stuck because he doesn't know how to do it. So he asks me what to do next. Okay, so then I demonstrate. All right. Is it clear? So sorry about that. I just screwed up. All right. So, but anyway, so this is how interactively tutor student. Okay. Now, so I'll now going back to my talk. So what I did is actually right. So I demonstrated 2 ways to teach semi student. Right. So one is I just demonstrate. This is the first one I demonstrated. I just demonstrated solutions. Semi student passively observed what I did. Learn from worked out examples. Okay. Here I never said no to semi student. Right. I always say do this, do this, do this. Okay. No negative examples. The second demonstration that I screwed up. Right. I interactively tutor semi student. Semi student does something, I say yes, no, right? Sometimes semi student got stuck, asks me to do something, right? That's interactive, right? That's we call tutor problem solving, okay? Now here, it's interactive, active learning because semi student actively commit to solve problems, and then I provide both positive and negative examples because I say no to semi student, okay? This is actually the key point of the day, right? Okay, so now, all right, I really have to speed up here.
No, the key point of today is what makes you think students will act like sim students?
I have trouble parsing your English.
What's that?
I have trouble parsing your English. Well, what's the point?
So, to me, the key point is,
yes.
I have a real student sitting here.
Yes.
What makes you think that real student acts like sim student?
Uh-huh. Oh, because
otherwise, all of the work with sim students is fascinating, but it doesn't shed much light on working with real students.
Not yet. Soon.
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 Real
Yes.
soon.
Thank you so much. You always ask their questions proactively, which is good.
Do you know Jerry Cornell?
No.
He wrote in Byte magazine 20 years ago.
Oh,
He had a
really?
phrase called "real soon now."
Yes. Yes. Okay. So, okay. I'm talking about the applications now. Okay, in next 30 minutes. I wonder if I have enough time. 3 major applications. Student modeling, teachable agent, intelligent authoring. This is the one I demonstrated now. Okay. Research questions, we have many research questions. We have quite a few publications. These are only the 3 things I picked up for the day. All right. Let me know if you're interested. I can send you more. Why do students make errors in algebra equations? Right, the students learning. Okay. Here, how and why students learn by teaching. Okay, that's this research question. Which learning strategy is better and why for intelligent authoring? Remember 2 ways to teach students? All right, so the first application. Student for student modeling. Here we are going to develop a theory of incorrect learning. Okay. So many of you may be a math teacher or want to be a math teacher. You know this is pretty common errors. One of the pretty common errors students make, right? So here, right, so I see -2, I do not want to see -2, I get rid of it, how? Subtract 2, of course, right? I know if I want to subtract 2 here, I have to do that over here. Yes, I do, okay? Because I get rid of this, the -2, it's gone. Because it's gone, I don't need equal sign anymore. Okay. Now I know this is -12. I'm good so far. Okay. Now I want to get rid of this. How? -7, of course. Right? I subtract 7. Right? So do the same thing here because that's what I have to do. Right? So it's gone. Now because I have only 2 things, I need that equal sign back here. Right? And then now I know I have to divide. Right? This is real, right? So maybe this part is not so common, but subtracting 2 here is very common, right? You may know this. All right? So we have a theory why students make this kind of error. Cynic student helps us to confirm that theory. Precisely speaking, cynic student helps us to fail to reject that theory. Okay? So you know that, right? All right. So the weak prior analysis hypothesis. Okay, we hypothesize that students make that errors because they have incorrect inductions. Okay, due to student learn incorrect productions due to incorrect induction errors. Okay, induction errors happen more likely when they have weak prior knowledge. So this is back to prior knowledge. Okay? All right. So example helps. Okay? Suppose you see this. Okay? 2x plus 3x equals 5. Your teacher told you it's gonna be subtract 2. When you see this, what do you say? You say, okay, I know I subtract a constant term. Obvious. Suppose your prior knowledge is pretty weak. You do not know the concept of constant term. What do you say here? You subtract.
The thing on the left.
Something like that. Yes, I would say a number. That also works. Okay? Things on the left also works. But I would go with this number. Okay? All right, so I'm good. Right? So now on the test, I see this. All right? On the test, right? So if I'm good, like I know the constant term, okay? What I do here, I see a constant term which is -4, right? By definition, right? So I subtract -4. Double negative. I can do that because I know the concept of constant term. Okay. What if I didn't know the term of concept of constant term? Do I see a number? Yes. What is the number? By definition, it's 4. By definition, to me, that's number 2, right? So I subtract 4. Okay, so that's my hypothesis of why students make this error. Okay, so the hypothesis actually says, okay, So get rid of this strong domain concept. Put some weaker version of that concept instead. Then you'll see a lot of errors that students commonly make. That's the hypothesis. We can do this because it's a student. It's easy to just replace these terms, right? It's like a brain surgery in some sense, right? We just replace these, all right? Now, that's the hypothesis. Okay, so I wanted to test the hypothesis. How? By using semi-student. I asked 12 semi-students to participate to this study, okay? So I control semi-students' prior knowledge. Like half of semi-students, 6 semi-students got brain surgery. They got replaced the knowledge. And the other 6 is just a healthy semi-student. We compared this, right? Weak semi-student and then a healthy semi-student, which I call strong semi-student. Here, semi-students, all 12 semi-students, they were all told by cognitive tutor Algebra 1, which is a commercial cognitive tutor. Okay? So here, that's an AI teaching AI. Right? The cognitive tutor teaching semi-student. Okay? So it's a totally 100% simulation study. Okay? Now, so the measurement is a validation, right? So we accuracy reproductions learned, and we also wanted to see the data fit. So we have data showing students' errors, right? And then we wanted to compare that with semi-student performance. Data came from DataShop, PSLC, Pittsburgh Science Learning Center. They have huge data, so we just do the data mapping. These are the few examples of the common errors that high school kids make. So you may notice some of these, right? Like, add 3 here for the minus 3 equals to 2 plus 5x, right? Which is not actually the solution, right? So our goal is to see how much of these errors students make. Okay, make, yes. So here again, right? 12 students, participants, they all tutored by Corgi tutor. Okay, these are the problems. Right? First problem, second problem, third problem. Each time they were tutored on a single problem, we tested student on 20 quiz problems. Okay, so it's tutoring on one problem, tested, tutoring on another problem, tested. It's pretty dense tutoring, testing iterations, which is impossible to do with the human students. Right? They hate this kind of stuff. Right? Now, here, the results. Strong, healthy semi-student, weak, brain surgery semi-student. Okay, these are the learning curves. These are 20 problems they tutored. Each time they tested, right? These are test scores. Okay, test scores goes up, which is good. But look at this. The weak semi-student is slower than strong semi-student. Okay, now, even this weak semi-student, that learning curve tends to be much quicker than human students. Human students go like this. Okay, so semi-student is still not exactly like human student. These are the errors actually that human students, the semi-students made. Surprisingly, it's only the weak semi-students who made this. No strong semi-students make all these errors. So here, right? So our hypothesis, I would say, is supported. Okay, only the weak semi-students make all these errors. All right, good. So the lesson learned: semi-students' theoretical contributions, right? So the weak prior analysis hypothesis was supported. Only weak semi-students made all these common errors. Both weak and strong semi-students made non-human-like errors also. It's a specific machine anyway, right? So the machine makes like this, something like this, right? Which never actually, the human being actually never do this. Adding 10 here is not that intuitive, right? But semi-student can do this kind of error, okay? All right, so the methodological contribution, semi-student can be used. I demonstrated that semi-student can be used to simulate students' learning, right? As you saw, right? And also semi-student simulation studies offer implications for students' learning. experiment, like we tried as theory. Okay, so these are the first demonstration. All right. The second one, the teachable agent. Here we are going to develop the theory of learning by teaching. Many people say, when you teach, you learn. I see. No, Roger. No. Do you believe teachers learn by teaching their kids? Obviously, do you believe? Yes, I don't. That's why I started this project. Okay. Now, I believe there's certain conditions under which they learn by teaching, not always. Okay. And I wondered how and why students learn by teaching. Okay. But conducting that kind of studies is pretty tough because of all these issues I mentioned at the beginning. Okay. Now, so to approach this problem, right? So researchers recently started to use simulation in the form of teachable agent. The teachable agent is a computer agent that you can teach, like sim student. Okay. So simply we just use sim student and then go to school, ask students to teach sim student, but actually they learn by teaching sim student. Right? Isn't that easy? Okay. My claim here is this. Because it's a online technology, we can collect a rich data, huge data, easily, which we call process data. Okay, it's an interaction data. Okay, we also have outcome data, which is usually the test scores, like pre-test, post-test. If we combine these two together, we can make a falsifiable theory of learning by teaching. That's our claim. This is a screenshot of the software. I can show you demo later if you like. It's pretty cool. Okay, it's called A+. I know everybody likes A+, right? So artificial peer learning environment using sim student, that's A+. All right, so here, I'm a student now, okay? I'm a student. I'm using this software to learn how to solve equations. My teacher told me my goal is to teach my sim student here, which is Fred, nicely, so that Fred can pass the quiz. This is quiz, okay? So I'm supposed to quiz Fred occasionally, right, as a formative assessment, right? So to see his improvement. Okay, so it's same, as you see, same interface, right? Actually, we just plug in that interface here, same interface, okay? But here again, don't get confused. Here, there's no tutor behind, okay? I'm teaching sim student using this interface. I'm a high school kid. No tutoring software behind, not at all, okay? Now, interaction is same, right? I provide the problem to sim student try to solve it. He suggests some steps. I say yes, no, right? Correct, incorrect. Sometimes sim student gets stuck, and then I do the same interaction. Okay. Now, what's unique here is that there's a theory of peer tutoring. It says if the tutee asks questions to tutors, then tutors tend to learn more. Right, so tutees challenge tutors, like, why am I wrong? Why did you do that kind of stuff? This is an example. Sim student in this context asks why questions to the tutors. I mean, student tutors. Okay? Here, sim student asking why am I wrong, basically. Okay? Okay, so now here, that's the quiz, right? So they are labeled here, right? So I gotta go to the easy level to the more advanced level, right? And then we do it locked here, right? Because students like to unlock things like this, right? So it's kind of motivational factors involved here, right? This is a teacher agent. He's here to actually summarize the quiz summary, quiz result like this. Okay, so I can see the result. Okay, so now I'm really running out of time, but yes, we go to school once every year so far. It's been 5 years. So we've been doing this for 5 years, and we went to school 5 times. So we have a lot of data. Okay, so, whoops. Oh, let's do that here. Okay. We are testing, understanding how and when students learn by teaching, right? So there are several hypotheses. We started from the very first one, which is the teachable agent hypothesis, asking, can we actually use computer agent for this kind of study, right? That's the first engineering study. It's a conference paper here. Second study is self-explanation hypothesis, like QT asking why questions that would help students to learn by teaching. That's the second hypothesis we tested. That was confirmed. Third hypothesis, motivation hypothesis. We hypothesized when students care about their SME student, right? When they really care about their SME students' proficiency, then they are more engaged to teaching. Therefore, they learn more by teaching, right? So here, to make their motivation increase, we hook up the game show. So for this particular study, students see their SME student and then their friend's SME student compete each other after they teach. Competing by solving challenging problems. So they wanted to see their SME student win, right? So it's kind of motivation factor here. It's external motivation, but it's kind of turned out to be interesting result. So that's the motivation factor. Fourth one is the meta-tutor hypothesis. You see this, like every year we do something like this. Okay. By this year, we are 100% convinced that learning by teaching, learning equation solving by teaching, never happens automatically. Why? Because students make errors. They teach students incorrectly, right? They screw up teaching, right? And then they couldn't actually pick up appropriate problems. They teach easy problems over and over again, right? Because that's the problem they can teach. So the student never actually pass the quiz, right? That kind of stuff. So we think that there must be a teacher agent involved in this environment, right? So that students can actually learn by teaching, right? Better. Okay. So here, this is the fourth study, the meta-tutor study, right? So here, that's the meta-tutor agent called Mr. Williams. You can click on this agent, right? So the pop-up menu here, right? What am I supposed to do now, right? So you can ask questions, right? So that this meta-tutor provides, for this particular study, meta-tutor provides a hint on how to teach, not on how to solve. Okay. So this meta-tutor provides feedback like, oh, now it's time to do quiz, or now it's time to teach that kind of program, right? That kind of stuff. This is a meta-cognitive help. All right, so the results, right? We have two types of tests. So it's like pre-test, and then 4 days of intervention. So 4 days they teach SME student, and then we have post-test. Okay. So this is the pre-test, post-test comparison. Okay. We have conceptual knowledge test, which is all about algebraic concepts like lifetime, variable terms, right? Kind of stuff. And then we also have a procedural skill test. This is all about how to solve equation. Okay. Now, as you see here, both type of tests, we see the jump from pre to post, statistically significant, right? But you don't buy it, right? Because the jump is pretty small, okay? So we are still disappointed here, okay? Now, procedural skill, we see the jump from pre to post only for the meta-tutor condition. When they have the scaffolding from meta-tutor telling how to teach, their score improve. Okay, so the meta-tutor hypothesis somehow supported here, okay, but not that much we expected. All right, so now here, this is the starting point of my talk today in 2 minutes, demonstrating the process data matters. Remember, this technology helps you to collect data, rich data. Okay, this is outcome data, right? Test data. Okay. Now, you may be wondering why we see such a small jump here. Why we don't see this baseline no learning? Why we see such a small difference here? all these questions can be asked when you jump into the process data. Okay, here, just an example. We wonder, did students ask meta tutor at all? Right, so that's the answer.
No.
It's no actually, but the 5 times, like just one single click a day, right? So it's pretty weak, right? So yeah, they didn't use. This is also an example of iterative design, the process design, iterative design, right? We know the current design does not actually work. They should ask metatutor a lot more, right? So maybe we can make this metatutor proactive. Metatutor say, wait a second, right? I have something for you, right? For example, right? Yes. Now, despite this relatively low frequency of metatutor usage, remember we still see a condition difference, right? So something must be happening here, right? So now, yeah, right. No correlation between the number of helper cases and the post-test scores, right? But still, right? Still we see the condition difference. What's going on? So remember the metatutor suggested what problem that must be tutored next, right? It's a type of problem. We hypothesized that if metatutors help hint on the problem selection worked, then we should see a notable difference between baseline and metatutor conditions in the way they pick problems, right? So we tested that hypothesis by simple regression. Okay, so this is the one step. There are one-step equation, two-step equations, and then the target equation, which is the equations with variables on both sides. Okay, so these 3 types the problems. We simply compute the percentage of each type, and then we just simply run a regression. Okay, and then well, this is not comparing the conditions, but at least for the metatutor condition. No, let me back up. No, this is for aggregated. This is for everybody. Okay, so it says that the more the 2-type problems they teach, the more the post-test scores. Okay, so teaching only one type of the one-step equation is not that good. It's actually bad. All right. So the process data tells you all these stories. Okay. So then, so we are positive that the metatutor's cognitive health should have affected students' problem selection. Now we simply plotted the type of problems, rank. These are the problem sequence, right? The first problem, second problem, the tutor. Y-axis here is a rank of the problem. The one-step equation is rank 1. Two-step equation is rank 2. The equation with variable size is rank 3. We simply computed the average rank here. Okay. So now this is the metatutor condition. That's the baseline condition. Okay. Now, if you see this here, right, and then here, right, see the slope difference. So this slope difference is significant, statistically speaking. So, right, so actually the metatutor condition students actually pick the higher level the problems quicker than the baseline conditions, right? Arguably because the metatutor helped to them to do so, right? Okay, so then lesson learned here. Theoretical contribution. We are still working on data analysis part. The presence of metatutor facilitated tutor learning, right? Knowing how to solve also affected tutor learning. I didn't mention this today, but we also have data supporting these observations. So we are positive that the tutor learning does not happen automatically, right? Because student tutors speak incorrectly without realizing they are making mistakes. And then students often fail to review study materials when they need it, right? So like examples, like You need overview, that kind of stuff. So they need like a scaffolding, right? The teacher agent should just come down and then just tell students how to teach. So the methodological contribution here. So semi-student teachable agent works for real students in real classroom. We can collect data using this technology, and then we can study from data. Right? That's a methodological contribution. Semi-student allows researchers advanced theories of learning by teaching, right, with its cross data. That's something I demonstrated today also. I didn't have a time to demonstrate this iterative improvement of the technology, but right, that the frequency of the better tutor help, right, seeking help has some implication. All right, so now I know I'm running out of time. I stop here, but I have a third application here, intelligent authoring, which I demonstrated right, today, right? So I skipped this, but this is a big picture. That's actually the old version, right? It looks pretty old, but right. So you make interface first. You demonstrate solutions using the interface. Right? Semi-student makes productions here, right? You have interface, production. That's the cognitive tutor. Right? That's what I demonstrated. All right. So so of course we have research hypothesis. We compared the learning strategies, but I do not really have time to mention this today. Okay, so here, let me just mention this. All right. So here again, we just asked how many students? This time we asked 40 students to participate in this study. Okay, and then we compared learning by tutoring, interactive tutoring, and learning from examples on the demonstration. Okay, 20 problem sequence here. Okay, that's also the test score. Okay, so as you see here, right, interactive learning is the winner. Okay, so we obviously went to the data, and then we recognized that authoring by tutoring, which is interactive authoring, provide explicit negative examples. Remember I said no to semi-student, which is explicit negative examples. That actually works. Okay, because of these negative examples, semi-student can revise the incorrect productions easily. But if semi-student only watches what I'm doing, it never realizes the productions are wrong. Okay, so the negative example really works here. Okay, so that's the lesson learned here. Now, watch this. If you replace few of these words, what do you see here? Right? Then this is an implication for students learning also. Right? So the learning, why learning by tutoring yield better productions? Right? That's because when you actually commit to the tutored problem solving, you make errors. Your tutor says no to you. You have a chance to revise your production. And so this is the implication for the students learning. Okay, so now, so that's actually the methodological contribution for semi-student, right? For the students learning. Okay, yeah, I'm sorry again, I'm running out of time here. So the conclusions here, right? So the semi-student is a computational model learning, right? It does the inductive the programming, right? And then semi-student helps researchers learn by teaching. And then also the semi-student helps researchers advance theory of learning. I demonstrated theory of the different strategies, the cognitive theory of learning by teaching, right? And then also and also I demonstrated semi-student helps us to collect data. Okay, all right. So now, as a take-home message conclusion, I would say that the seniorest learners with cognitive fidelity really matters. I say COG5, simulated students, right? They can actually help us to conduct education studies to make theories. Okay, so now I would say 20 years after Cut Van Len, I would say that technology for cognitive assimilation of learning is now mature to produce and collect reliable data to understand how students learn. Okay, so now I have quite a few ideas about the future directions. If you're interested, let me know. We may be able to work together, right? All right, so yes, so thank you so much. And if you have any questions, let me know.